Hi there, folks. In this video, I'll be talking about atomic mass spectrometry. Now, this provides highly sensitive elemental analysis, and some of its advantages over the optical spectrometric methods that we discussed previously are that it has up to 3 orders of magnitude lower detection limits, so it's very sensitive, it's easy to interpret spectra, and it provides high resolution, as well as precise mass definitions, which enable atomic isotopic ratios to be measured. So for example, carbon-12 and carbon-13 can be distinguished because they have different masses. However, some disadvantages are that the instrument costs are 2 to 3 times higher, there can be significant instrument drift, and there's also some interference effects. Now, before we dive into atomic mass spectrometers, just 2 terms we have to define. So atomic masses, instead of using the standard atomic mass scale, mass spectrometry uses the unified atomic mass unit, which is also known as a Dalton. So 1U, which is the unit for atomic mass unit, or unified atomic mass unit, is 1/12 of the mass of a neutral carbon-12 atom. The other term is the mass-to-charge ratio, either of an atomic or molecular ion. And this is the ratio of the mass number, m, to the number of fundamental charges, z, on the ion. So mass to charge, m over z. But because most ions are singly charged, i.e. z is equal to plus or minus 1, the mass to charge ratio is usually just the mass number of the ion. Now, some atomic mass spectrometry analysis, it contains the following steps. So first you have to atomize the sample. Then you have to convert those atoms into ions. And note these are the same steps that we used for atomic absorption spectroscopy and atomic emission spectroscopy. Then you have to separate the ions based on their mass to charge ratios, and this is done using a mass analyzer. And then finally you have to count the number of ions of each type, and this is done using the detector. So this table here shows the different types of atomic mass spectrometry, and note that the first 3 entries here are actually something called hyphenated methods. Just write that down. And this means that two different instrumental techniques are combined in order to provide more information, and we'll see this again in the chromatography section later in the course. So mass spectrometers produce ions and separate them based on their mass to charge ratios. And we're going to look at 2 different types, which are defined by their mass analyzer. So the mass analyzer here, which sorts the ions, is sort of the heart of the instrument. And the 2 types we'll be looking at are the quadrupole mass spectrometer, and the time of flight mass spectrometer. And so in this figure here, you can see the main parts contained within a mass spectrometer. You have an inlet, which just ensures that a very micro amount of sample enters the instrument. And then ionization occurs either by a bombardment of a small amount of sample with electrons, photons, ions, or molecules, or by applying a some thermal or electrical energy. Then you have the mass analyzer, which is analogous in a way to a monochromator and an optical spectrometer, in that it's sorting the ions instead of sorting the wavelengths like it would be in optical spectrometry. And then finally, you have the ion transducer, or the detector. And there are several different types, but we are going to focus on the electron multiplier. And it's a dynode-based electron multiplier, so very similar to a PMT or photomultiplier tube, but instead it collects and converts positive ions into an electrical signal. So each dynode is held at a successively higher voltage. So these are the dynodes here, and this is just the same as it was in a PMT. But the cathode and dynodes have a copper beryllium coating that readily emits electrons when electrons or ions strike the surface. So because the electrons are attracted to each successive dynode, because they're held at a higher and higher voltage, So if every time it strikes the dynode down the chain, it results in a huge number of electrons for each ion that strikes the cathode initially. All right, so the first mass analyzer we're going to look at is the quadrupole, and it's the most common type of mass analyzer or mass spectrometer that's used. So in this, there are 4 parallel cylindrical rods that serve as electrodes, and each opposite rod is connected. So one pair is connected to the positive side of a DC or direct current source, and the other pair is connected to the negative terminal of this DC source. So here you can see that these pairs of rods here are alternatively positive and negative. And then in addition, a stronger AC or alternating current field is also applied to each pair. And in the diagram here, they call it RF or radio frequency, but also known as the AC voltage. So meanwhile, first off, the ions are accelerated between the rods by a potential difference across the whole thing. Meanwhile, the AC and DC voltages are increased at a constant rate. And so this means that all ions except those with a certain mass to charge ratio strike the rods and therefore do not make it to the detector. So let's take a closer look at these ion trajectories in the quadrupole. So in the absence of a DC voltage, with only an AC voltage or alternating current voltage applied, which is therefore alternating between positive and negative, at point A here, so during the positive half of the AC cycle, positive ions will converge in the center of these quadrupole pairs. However, during the second half, at point B, where there's the negative half of the AC voltage, they're going to diverge. Now, whether a positive ion strikes the rod depends on its rate of movement, mass to charge ratio, as well as the frequency and magnitude of the AC signal. So now if we apply a DC voltage, which is superimposed on this AC voltage, we know from physics that the momentum of an ion is directly proportional to its mass. Therefore, it's more difficult to deflect a heavier ion. So ions that are too heavy will not have moved far enough from the positive rod before it becomes negative again, and therefore it's going to be attracted and it's going to crash. On the flip side, ions that are too light will crash into the negative rod before its polarity changes. Therefore, it's this very tricky balancing act. In order for these ions to make it through the quadrupole rods, an ion needs just the right mass to charge ratio in order to be successful. Now, to scan a mass spectrum in this quadrupole instrument, the AC and DC voltage are increased simultaneously while their ratio is kept constant. And this single sweep can take only a few milliseconds. So the second type of mass analyzer we're going to look at is the time of flight mass analyzer. And in TOF instruments, the time required for positive ions to travel from an ionization source, shown here, to the detector is measured. So a pulse of analyte ions is accelerated towards a field-free drift tube. And because they're, in theory, all arriving with the same kinetic energy, their velocities vary inversely with their masses. And so the lighter ions are going to arrive at the detector sooner than the heavier ones. So the design shown in B of this figure down here, which uses a reflectron, is just increasing the resolving power, allowing for rapid data acquisition. Now, the cons of this time of flight mass analyzer is that you need really fancy electronics in order to monitor the detector signal in real time. And it's also not as sensitive as a quadrupole mass analyzer. However, you have a virtually unlimited mass range, in addition to it being very quick, having a very high time resolution, and it also is very simple and rugged. So at the end of the day, mass spectrometers result in very simple mass spectra. As you can see in part B down here, this is the mass spectrum of cerium. You can see that the two different isotopes are very clearly resolved in an overall very simple spectrum. Now you can compare this to the atomic absorption spectrum as shown up here. Put MS here. And you can see that the atomic emission spectrum of cerium is much more complex, and it's very difficult to resolve all of the different cerium peaks. And in addition, you don't know what their isotope and what their mass is.